bit of information. I do not bite people who ask questions. So this entire week, I'm here for you, and I'm here to teach you stuff. I'm not here to demonstrate that I know stuff. I have already demonstrated it well enough. So the most important thing is don't hesitate to ask me questions during the lectures, between the lectures and program, at any point in time. Stop me, talk to me about anything you're interested in. I'll be more than happy to answer. I'm here for you. So if there's anything unclear, if there's any moments where you feel like, okay, everybody gets this, move on, or quite the opposite, if you are like everybody is lost and you are scared to tell me, please somebody speak up and let me know. Okay, so what I have prepared for you this week is a series of lectures on various topics, and yeah, most of the things I will be talking about will be somehow related also to programming competitions, but in general, I think that one of the important parts of what we are doing here and why everybody of us is interested in these competitions isn't the actual competition itself only, but the most important thing, at least for me, has always been the understanding, the seeing of the connections and the patterns and being able to analyze problems and seeing what exactly makes or carrying various kinds of problems difficult or easy, and yeah, what are the patterns in problem solving. I think that is very close to my heart, and this will be like unifying theme about everything I will be talking about. The stuff I'll be talking about will be the stuff I'm passionate about, that I like, that I think I understand well, and the passion, the interest, the ability to like play around with things and have joy from it is what is, I think, important for making progress and becoming better at problem solving or algorithms or whatever you want to call it. So yeah, for today's lecture, I have selected a topic that is kind of self-contained. I will be talking about game theory. In particular, at the beginning and for the at least first half of the lecture, it will be combinatorial game theory, but then, depending on how much time you have, I will also branch off to some other areas. And the reason why I selected this for the first lecture is because this is kind of approachable to everybody in a very similar way, regardless of how advanced you are, what exactly your background is. Yeah. Afterwards, we will have some contests. For the first two contests, the problem sets I prepared are taken from previous individual contests we had, and if it's possible, I would also then ask you to solve the first two contests individually, and like also to give me some kind of a better calibration, like of what is the distribution of skill levels, and I can then try to tweak my future lectures. I have selected two more lecture topics I'm pretty sure I will be using during the week, but I'm also willing to be somewhat flexible with the topics of the rest. So again, if you have something that many of you would really like to hear about, talk to me about it during the breaks. Let me know that these are the topics that really, really interest you, and I'll see what I can make happen during the week. Okay. Regarding the technical details of the contests, we will probably deal with this before the actual contest. That's probably the easiest way to do the logistics. So right now, let's go directly to talking about game theory. All right, and when we are talking about games and trying to analyze the games, and usually the big question we are asking, like, given these rules, who will win the game? What is the winning strategy? These are the big picture questions we usually ask. The first very important step that is sometimes neglected is making sure we understand the rules. And this is not always trivial. How many of you do play chess? Almost everybody, excellent. How many of you do know the rules for castling? This is the move when the king and the rook kind of swap places. Okay, can we collectively tell what the rules are? Just shout out and say some bits and pieces out of it, sir.
The king cannot move, the rook that you're castling with cannot move, and the squares that the king moves through can't be attacked by an opponent's piece.
Yeah, so yes, there were very important bits and pieces there. They were all correct. So In order to castle, we pick up the king, and we move it 2 steps towards the rook. The king cannot cross through an attacked square. It has to be safe for the king to do so, and then after the king does the 2 steps, we then move the rook and place it on the middle cell the king just passed through. And that was the important bit, that the king must not have moved since the beginning of the game, and also the rook we are using for castling must not have moved since the beginning of the game. Is this correct? Is this complete?
In check, yeah.
Yeah, you can also, yes, the king also after the 2 steps cannot end in check. Yes, that's correct. Is it now correct and complete? Okay, so about 50 years ago, this is how the rules were actually written in the official tournament rules for chess. And then came a guy called Tim Krabbe, and this guy is pretty famous for many things around chess. In particular, like different like composition chess puzzles and asking questions like, can we set up a configuration on a chessboard where it is a forced mate in 1, and all the moves the white actually can make will mate the black, and what is the maximum number of such moves? How can we set up the pieces so that there's like 17 different moves or 20 different moves and all of them are checkmate? And one of the puzzles he came up with look approximately as follows. So this was one of like the standard chess puzzles. So you are given a position on a chessboard and asked the question that white has to win in, let's say, 3 moves, and you have to find a way how to do this. And in this particular puzzle, there was a white king in his original square. There were white rooks in their original squares. There was a white pawn here, and there were some other pieces here and there. And using normal chess rules, there was no way to do actually the mate he was asking for. But there was still a way, and the intended solution was like this. You walk with the pawn, you get the pawn to the top row, you promote it, and instead of making a queen, you under-promote it to a rook. And what you get now is a king that is in its original position and hasn't moved since the start of the game. And you have a rook that hasn't moved since the start of the game because it just appeared. And now, according to what the rules of chess were back then, it was a valid move to move the king 2 steps here, to move the rook there as a really, really long castle. In the official solution, the short castle and the long castle are denoted like this, so he wrote it like that. And this actually forced the change in the rules of chess, that when it was specified that only the rooks that are there from the beginning of the game can be used for castling. So attention to detail when looking at the rules is also quite important. Okay, so when it comes to all kinds of games and puzzles, the first thing that matters is the number of players. There are some games and puzzles for a single player, and I will be talking about these first in a moment. There are some games and puzzles for 2 players, and for these we have really an awful lot of theory behind them, and we know a lot about what's going on and how to analyze various kinds of games like this. And then there are games that involve more than 2 players. And as soon as you have more than 2 players, it's all kinds of messed up. It's usually like almost everything is undecidable, and yeah, it's not really possible to analyze it in terms of optimal play. And not just because like politics coming into play. Yep. Like one of my favorite pastimes is I play Magic the Gathering, and one of the formats in which you can play this Commander, which is like a multiplayer free-for-all game, and what always comes into play during those games is politics. If there is somebody who seems to be winning, then everybody like teams up against them, and so on. And capturing these kinds of analyses and doing this with the games is almost impossible to do mathematically. But even if you have like individuals trying to play optimally and trying to win games, analyzing anything with more than 2 players is borderline impossible. So even also in today's lecture, the stuff I will be talking about will be the reasonably approachable stuff, 1-player games and puzzles and 2-player games. So starting with the 1-player ones. So I think everybody here has solved some Sudokus and similar puzzles, and these kind of pen and paper puzzles are the first category of things that are worth considering. And some puzzles are reasonably easy, some puzzles are difficult, and there is a very natural question to ask ourselves: what exactly makes these puzzles difficult? What exactly makes puzzles interesting to solve? If you are 5 years old and you pick up a magazine for kids of your age, you will sometimes find puzzles appropriate to your age, like find the path through a maze. And when you are 5 years old, this makes fun because you don't know anything about like your algorithms on graphs, and so you like do trial and error, and eventually you find the path. But once you learn how to do this, it becomes kind of boring, and at this age, you will probably not be willing to do many mazes in a row and solve them by hand because it's repetitive, it's applying an algorithm you already know, and you are not really challenging your brain to do anything interesting. On the other hand, already, for example, basic Sudokus can be quite tricky to solve. There are some like beginner techniques where you can, if you see a box that has 8 numbers and the 9th one is missing, you can fill in the 9th one. But there are more and more techniques and tricks you can discover as you learn how to solve them. And in fact, during the lockdowns, a channel on YouTube, Cracking the Cryptic, became very popular, and I believe some of you have seen some videos from it, which is 2 British guys solving either cryptic crosswords or these kinds of variations of Sudoku puzzles. And these are made by humans to introduce new and new tricks of finding out the new pattern, finding out the new way of analyzing something and seeing what's happening in a position, and making like new types of logical deductions. And this is what makes fun for the solvers. And why can you do this in one type of puzzle but not in another type? It turns out to be the case that for many of these pen and paper puzzles of the type of Sudokus, you can actually show that the underlying puzzle, if you generalize it to general sizes, and if you try to program a computer to solve those problems, the interesting ones generally turn out to be NP-complete. So this is something in theoretical computer science. NP is a class of problems that are solvable in non-deterministic polynomial time. What this means for real-life computers is that if you are already shown the solution, you can verify it in polynomial time. This is usually very easy, very straightforward for these pen and paper puzzles, because what you are doing when you are verifying the solution, you are just checking whether all of the rules have been satisfied. For a Sudoku, is each row exactly complete, each column, and so on. So does every region have exactly the numbers 1 through 9, and are the starting ones in their correct locations? And if you have some other things in the puzzle, like maybe lines, thermometers, or other fancy stuff that is being used in the modern Sudokus, then also verifying that those are satisfied. But this is all very easily mechanically done, and what this means is that solving this puzzle belongs into NP. And there is the probably biggest question of today's computer science, whether P equals NP, so whether everything we can verify in polynomial time can actually be solved in polynomial time. And we don't know. This is an open problem. This is worth not just $1 million, but also a lot of fame if somebody can actually crack this. At the moment, not 100%, but majority consensus among scientists is that P doesn't equal NP, so it's the more natural outcome. The puzzles are actually hard. In practice, what this means is we do not have any polynomial time algorithm that would solve any of these hard problems. So in general, you have the reasonable guarantee, so when you use this as a puzzle for actual humans, that there is no one single strategy that can be learned and applied and used to solve each and every puzzle. So, for example, another kind of puzzles that can become very boring and mechanical after some time. I got lost in the middle of the sentence, sorry. Just erase it back. Okay, so I have been doing in the past some research into this area, and I was interested in these questions like what makes puzzles interesting for humans, and how can we, for example, here's a more advanced question you can ask, how can we kind of automatically grade the difficulty of a puzzle? So if you have, for example, some Sudokus even created by humans or maybe even auto-generated, how can you judge how difficult they will be for a human solver? Or how can you automatically generate the statements of various such puzzles? So these were things I was looking into, and one of the biggest points I learned about it was exactly this observation, that the interesting puzzles usually generalize to something that is NP-complete, that will force you to solve this particular instance of the puzzle instead of solving the puzzle as a whole, or finding the algorithm, and this is what keeps the human interest. And okay, so this is what you can do with a pen and paper, but yeah, nowadays everybody has in their pocket a computer much more powerful than everything that was used for the first moon mission, for example. It's called a cell phone, and on the cell phone you can play games. You can also do it on your computer. And many different puzzles and these types of games have been created throughout the years. One of the most famous puzzles of this type that we are currently interested in is the puzzle Sokoban. And you have probably seen this after various different names, and this is the puzzle where you have a grid. On the grid you have some boxes, and then you have one single guy that is in charge of this warehouse, and he can push the boxes, but if the box he reaches a wall, then of course he cannot pull it away from the wall, he can just push it. He can then walk around it and push it in another direction. And there are some prescribed locations for the boxes, and you have to push the boxes to those locations. How can we solve puzzles like this one on a computer algorithmically? So one very important lesson that will be used throughout the rest of the lecture today is that we can view any kind of a puzzle like this as a state graph. So at any moment, we have a state of the puzzle. So when we are describing the state of the puzzle, we have to say about all of the movable pieces. So in case of Sokoban, about the worker and all of the boxes, what exactly are their current locations. And once we do this, we have the description of the current state. And from each and every state of the game, there is some possible set of moves. In case of Sokoban, the moves will involve the player moving one step up, down, left, or right. So there are at the most 4. A few of them could be impossible because of the walls. So from any state, we have at most 4 moves, and these moves bring us to new states. And this entire thing can be viewed as a one giant graph. And in this one giant graph, we are asking the question, what is any path, or maybe even what is the shortest path from the initial state to any state in which the entire puzzle is solved, in which all of the boxes are on their correct locations. So this gives us a baseline approach that can always be used, which is very simply a breadth-first search. We have a graph, we are asking a question about the path existing, so we can do any kind of a search on the graph and go from here to there. There are some, once you have the baseline solution, we will realize that for the traditional Sokoban, this can solve like maybe the first 1 or 2 levels. And what happens afterwards is that the state space simply becomes way too large. So the algorithm works, the theory is correct. There is only the problem of not having enough resources. So we will very quickly run out of memory, and even if we can deal with the memory issues, we will run out of time because of how many of these states there are. So if you have like 50 free squares in a level, and there is a single box, then you have 50 positions for the box. If there are 2 boxes, then you have 50 squared positions approximately. If there are 10 boxes, there's 50 to the power of 10, and yeah, suddenly it's a really huge number that is kind of hard to examine. So when you are trying to solve these bigger instances, trying to come up with a more clever algorithm, again, there are some standard techniques what you can do. One of the things you can do is make observations about symmetries that help you reduce the state space. So for example, in Sokoban, it doesn't make sense to have the boxes numbered and to store the state saying that position of box 1 is this, the position of box 2 is that, and so on, because the box numbers don't matter. Any box can end up in any of the final locations. So we can reduce the state space by about a factorial of the number of boxes by simply always sorting them from top to bottom. So we will have a sorted list of box positions, and only this will be the description of our state. So what we just did is we discovered that some of the states in the original state graph are equivalent. The answer for them is exactly the same. So we can represent them by just one of them, the canonical representation of all of these states. And in this case, it's by sorting the boxes. And this doesn't apply to computer puzzles only. One other very famous puzzle, maybe the most famous puzzle ever, is the Rubik's Cube. So this is the 3x3x3 cube. You can rotate the faces, and each face has a single color, and you are supposed to return it back to the unscrambled setup as quickly as you can. And this is, again, something that's really crazy if you look at the world championships in solving Rubik's Cubes. They are using special models that are really well oiled to turn really nicely, smoothly, and the best guys can do it in a few seconds. Really, it's well, the records are well under 5 seconds now for traditional 3x3x3 Rubik's Cubes. It's pretty crazy what the human brain can do. But anyways, Rubik's Cube, when we are trying to solve it algorithmically, you can again use this exact same approach. So any specific configuration of the Rubik's Cube is a state in which the puzzle is currently located, and each and every transformation, each and every rotation of a face of a Rubik's Cube brings you to a new state. There are some differences between Sokoban and the Rubik's Cube. What is the most notable difference in terms of the graph? Precisely, that's the answer I was looking for. The Rubik's Cube moves are reversible. If you can make a move, you can always undo the move. So when representing the Rubik's Cube as a state space, as a graph, the graph can be undirected. So the edges go and are usable in both directions. In Sokoban, you don't have an in-game version of a move backwards. So when you push when you push a block, then you don't have this follow-up move that will get you to the previous situation again. So for Sokoban, the graph has to be directed. And yeah, for your Rubik's Cube, you can now again ask very interesting questions about this graph, like what is the shortest number of moves necessary to solve each and every configuration? And yeah, the Rubik's Cube turns out to be just so big that this answer was possible to be answered, and this was already done a few years ago. And I personally know a few of the guys that did this, and they have been also for many, many years members of this programming contest community. So they came from this background, and at some point they asked this question. And it required two steps, the answer to this question. The first step was they did a lot of math on paper, and they played around with various kinds of symmetries and reducing the size of the state space. So there are not just the obvious symmetries, like when you have the cube in your hands, you can rotate the entire cube, and you are still getting the same state with the same answer. So if you just flip it upside down, the number of moves you have to perform to solve it doesn't change. This is obvious. But you can then do some more advanced reasoning about what changes if you swap some regions among themselves, and you can argue that this also doesn't influence the final answer. So what they managed to do is they managed to reduce the search space needed to just about the right size, that if they had a few months of computer time, they would be able to go through it all and run essentially a smarter BFS to examine all of the states and find out what the answer is. And then they got Google to donate them computation time on some of their machine clusters. So they actually did run this search, and they did come up with the answer that the God's number, they call it, for Rubik's Cube is 20. So any configuration of a Rubik's Cube can be solved in 20 moves or less. And there are actually only very few of those specific ones that require those 20 moves. And we know all of them, and we know what's happening on the hardware end, and there is too much going on in the middle to be in any ways interesting. So yeah, programming contest community gave us the people who came up with these ideas and actually went through and got this search done. So that's what you can do in problems like this. And there is a bunch of techniques how you can also on your own, when you are trying to solve some kind of a game or puzzle like this, what you can do with the game graph. So among the techniques you should eventually learn on your own how to apply is, for example, the idea of doing the standard BFS, but doing it in both directions at the same time. And this type of puzzles like the Rubik's Cube or Sokoban or puzzles like this are exactly the type of puzzles where this bidirectional search really gets to shine. So what is going on there? What's the idea? So suppose you have one single starting vertex. So this is the initial configuration, a scrambled Rubik's Cube or a level of Sokoban in its initial state or whatever you like in your other puzzles. And somewhere on the other end of the graph there is one or more of these target states that you are trying to reach. And now the issue with this graph is that as you start from any vertex and you start doing the first move, then the second move, then the third move, is that almost all of the combinations of these moves, at least initially for the first n steps, they are creating new and new configurations. So you take a Rubik's Cube and you rotate one face and then you rotate another face. Almost all of these combinations will produce, or I think maybe even all of these combinations will produce different scramblings of the new Rubik's Cube. So if in any configuration, if in any state you have d possible moves, then at distance 1 you will have roughly d new states. At distance 2 you will have roughly d squared of them, and so on. So as you are increasing the number of steps you perform in the game, the number of reachable states essentially grows exponentially. And if the shortest path happens to have the length L, then your breadth first search will have to visit essentially d to the power of L vertices. So as we are running the BFS and the distance from the start increases, the number of states in the queue, the number of states processed is growing exponentially like this. And now the trick that you can do in any problem you see like this, and this is purely mechanical, this is the thing that applies all of the time, is instead of running the BFS just from the start, you can do two separate BFSs running as if in parallel using two different colors. So in addition to having the black one starting from the start, you also have a blue one that will start at the finish, and will, if this is a directed graph, it will be using the edges in the opposite direction, so going against the direction of the arrows on the edges. And now what you do is you do one step from the start, and then you do one step from the finish. You process all of the neighbors of those vertices from the start, and you process all of the neighbors from the finish. And eventually, these two sets of explored vertices will meet, and they have to meet on one of the shortest paths. So the first moment when we color a vertex both black and blue is the moment when we discovered the shortest path from start to here. We discovered the shortest path from here to the target. And given that we have already processed everything that was in smaller distances, we can have the obvious guarantee that this particular moment has to be the discovery of the actual shortest path from the start to the finish. And what happened now is that both from the start and from here to the finish, we only had to explore everything until the distance approximately L halved. So instead of d to the L, we now have twice d to L half, and this is a very, very significant reduction of the state space. So if this is maybe 4 or 10 or something like that, and again, so this makes twice the distance approximately still viable to search. So if you have a puzzle in which each step has 10 different possibilities, then with the original BFS, you can find the shortest path between the start and the end if they are reasonably close to each other. If the distance is 8, then you will visit roughly 10 to the 8 different vertices before you find the path here from here to there. Distance 9 becomes like the borderline where it is feasible still, because 10 to the 9 states having in memory, this is already several gigabytes. So on a personal computer, you can probably still squeeze it in, but it will require some more careful coding already. And 10 is already probably impossible on standard computers. And this optimization of going in both directions at the same time brings you from distance around 9 to distance around 17, 16, 18, because simply you just need two balls of this. You can have two balls of the size that you previously had one. Yeah. So this is a very standard trick. And then there is a whole plethora of approaches that are based on trying to do some heuristic optimizations. So instead of having mathematical guarantees like here, most of the state of the art in terms of finding shortest paths in the state graphs will use some kinds of heuristics, and will use an algorithm that is called A star or some variations thereof. So the idea here is that when you are going from A to B, for example, you are trying to route some kind of units in a real-time strategy game. So there is a unit here, an A, and you selected it with a mouse, and you click that it should attack some building that is here at B. Now the game should direct the unit to go from A to B. And again, we could do this using some standard BFS to find the shortest path for the unit. But we can also do some optimizations. So suppose we already explored some surroundings of the vertex A. Now for each of these nodes on the boundary, we not only know the exact shortest path to reach there, but we can also estimate from below. We can give a lower bound on the remaining distance. And the very easy lower bound in a grid, if we can move only up, down, left, and right, is the Manhattan distance from where we are to the finish. So if there are no obstacles at all, this is how long it will take us to reach the finish from there. And there is a mathematical guarantee that we cannot do this faster. And the basic idea of this type of algorithms that are called A star is that when you have the queue, you will not have it sorted based on just the distance so far, which is what you would do with BFS or Dijkstra's algorithm, but you will keep it sorted based on the sum of the distance so far, that is exact, and the lower bound on the distance to the goal. So the most promising candidate will be on the top of the queue always. And this is the one you will take out, process, and push the neighbors back into in this type. It will already be a priority queue sorted by this type of priority. And what turns out to be the case is that this very, very severely can limit the actual search space, the space of vertices that will get visited by the search. And the closer the actual path resembles the lower bound estimates, the fewer vertices you will actually need to expand in the graph. So in a real life map with some obstacles here and there, the set of visited vertices by BFS would be essentially everything, and the set of visited vertices by A star will be the optimal path and some surroundings around it. And again, this is not just for fun or just for writing computer games, but some generations of map software were really based on these ideas. And to this day, one of the two best approaches for static maps and pathfinding in static real-life maps is essentially starting with this type of approach and then applying some more algorithmic optimizations on top of that. This is the one that eventually lost. And why was this the case? So there was a time some years ago when if you opened a map application like Google Maps and you said that I want to travel from A to B, find me the shortest path, that something that started with this idea and then got some more and more algorithmic improvements was actually what was used to give you the answer. And for those types of maps, it was really very good, and it was reducing the search space essentially to just very few nodes in addition to those that you need to produce the path. So it was very quick. Why did it lose to another approach that was
kind of more hierarchical based and making like a series of abstractions on top of the graph, the availability of real-time traffic info. So the heuristics, the optimizations that were used for this type of approach were mostly based on pre-computation of some other useful information about the graph. You could have some kinds of like waypoint heuristics and stuff like this. This kind of stuff that needed to be pre-computed was essentially less and less usable when we are trying to route the vehicles according to real-time traffic information, that this edge of the graph suddenly has a much bigger weight because there is a traffic jam. And the other approach turned out to generalize better to these kind of things. So, yeah, this often happens that if we start with just playing around with some puzzles and exploring them and using them to learn some new algorithmic ideas and techniques, it turns out to have very interesting practical applications as well. And in fact, a lot of what we are doing in programming competitions is exactly this type of like preparing ourselves. We are taking interesting algorithmic ideas and we are condensing them as problem setters. We are condensing them into the purest form of just focusing on this particular algorithm, on this particular idea. And the fact that this ends up being a toy problem, it ends up being a puzzle that is not useful at all on its own, doesn't really matter, because what really is useful and important isn't this toy setting we are using for the problem, it's the underlying idea and then the generalization thereof and seeing it as a pattern in problems. Okay, so back to the state graphs, back to Sokoban. When I was talking about pen and paper puzzles, I made the assertion that what makes them interesting for human solvers is the NP completeness. So is Sokoban NP complete? And the answer is not just yes, the answer is yes and. Sokoban is even harder than NP complete. Sokoban has been shown to be p-space complete. What this means is that you can actually assemble levels of Sokoban that consist of various gadgets, various small rooms that are arranged in such a way that, for example, there is a room that forces you to pass through it only in one direction. There is a room that can be used like a crossing, that you will have a room, there will be some paths entering it like this, and there will be some boxes and rooms arranged inside of this region of the puzzle that force you that if you enter from the top, the only way to leave this particular block of the puzzle without actually pushing some box into the corner and making the puzzle unsolvable is to push the sum of the boxes and then leave from the bottom. And if you enter it from here, then you have to leave it from there. And once you come up with such a design of a part of the puzzle, then you can use this as a bridge in your construction of a level. So if you want to send the player from A to B, and at some other point you want to send the player from C to D, and you don't want them to take a corner and go to some other unallowed part of the level, this suddenly makes the design easier because your wires in the puzzle can cross. And using gadgets like this one, it is actually possible to construct Sokoban levels that correspond to computers with some fixed amount of memory. There are some specific rooms in which the position of the box, whether it is currently blocking or not blocking the exit, can be seen like a storage of one bit of information. And in order to solve the level, your player has actually to run around the level and simulate the steps of this particular computation of this particular computer. So there is a hardwired instruction set, and based on this, how he can currently pass through a region that is encoding the program of the computer, he will then appear on the exact right spot where the action is currently happening. The computation will simulate the next step, and so on. So there can be levels of Sokoban where the solution is actually, the solution itself, the number of steps, is exponential in the size of the level. And having this particular construction means that this is kind of among the hardest problems of this type. So the hardest question for this type of problems is you have something what's called a Turing machine that is bound to the size of its input, And for this machine, you are asking whether it accepts or rejects the input. This is a very hard question to answer, even harder than the NP-hard problems. And we can reduce this question to solving Sokoban. So Sokoban is as hard to answer as this. Yeah, and you can do similar type of stuff with many, many other puzzles and computer games. So, for example, you can create levels of lemmings that are exponential, so they require exponential time to be solved with just some small subset of these lemmings. That you can build a bridge to cross, and then you can dig through the bridge to drop through a hole, and you can be forced to make these decisions optimally to get exponential to solve some kinds of levels. You can do one of my own publications on some of these conferences that deal with these puzzles was that you can do very similar stuff in Prince of Persia. So Prince of Persia is the very, very old platformer that has since had multiple releases, and you have the character that is running around. And the important thing here, sometimes there are doors that can be opened or closed, and sometimes there are pressure plates that can be used to open or close those doors. And as soon as you have some things like this in your particular programming game, computer game, then suddenly you can use the state of those doors as a memory of your computer again, and you can force the player to go through just your selected set of passages, because otherwise there will be too big of a jump or something, or too big of a fall. And then you can assemble a level of Prince of Persia that kind of beats the purpose of the original game. The original game was designed to be a platformer where you jump and grab on ledges and sometimes sword fight, and then you reach the goal and save the princess. But pesky computer scientists like myself asked the question, what are the hardest levels of Prince of Persia we can assemble? And the hardest levels, again, can force you to answer questions like, here is the general program that is using some limited amount of memory, and tell me about this program, does it accept or not? And your only way of solving the level is actually exponential in length, and involves actually running the program until it accepts. And if the program accepts, then you are then allowed to open the final door and leave the level. So yeah, computer scientists are weird. We sometimes, instead of playing, we ask weird questions like this one, and then we answer them because it makes fun. So again, if we have these puzzles, on one hand we have some basic approaches, what we can do with them, searching the state space, and we can do optimizations on top of that, search the state space smarter, and try to squeeze it into the time and memory we have available. But on the other hand, for many of these puzzles, and nowadays you can already do some generalizations, so as soon as a computer game has this particular set of properties, that you have some kind of door opening mechanisms and so on, then depending on how they work, you can duplicate these kinds of constructions we did for the earlier games and make the same conclusion that these are, in general, algorithmically very hard to solve. So if you want to solve Sokoban automatically, if you want to write a Sokoban solver, you will be on the it is very, and several more very in the sentence, is very unlikely that you will come up with the polynomial time algorithm that actually does this for each and every possible input. So for the best possible Sokoban solvers that we currently have, the situation is such that they contain a series, a collection of heuristics that are helping in specific situations, and they are trying to do as much clever stuff as we could come up with, and to optimize the search as much as we can, and then we hope that the particular instances we are trying to solve actually will fit into the time and memory we have available. And this is also what is going on in the world of NP-hard problems. And nowadays we have like two very good, very practical tools when we encounter these problems in real life, and we have to solve them. So if what we are asking is a yes/no question, does this particular NP-hard problem have a solution or not? There are tools called set solvers. Set is one specific of these problems. it means satisfiability. And in this problem, you have a Boolean formula, and you are asking whether there is an assignment of truth values to the individual variables that appear in the formula such that the entire formula evaluates to true. And one of the very first results that was like the founding stone of NP completeness was the result that anything that is in NP can be encoded as such a logical formula. So if you had a tool that can answer satisfiability of Boolean formulas, you could use it to solve any of these problems. And this made it very natural to focus on solving this particular type of problems, to do optimization specifically for solving, for finding a truth value assignment to a set formula. Yeah, and yes, just to give you a better idea of what's going on, imagine that you have a Sudoku. How do you encode a Sudoku into a logical formula? You can have logical variables for each cell and each value. So you will have a logical variable that is saying cell in row 4 and column 7 contains the value 8. And this variable is either true or false. And now you will write down a set of formulas that correspond to the rules of Sudoku. So for each cell, exactly one of those variables is true. So the logical OR of the 9 variables for this particular cell has to be true. And at the same time, the logical AND of any 2 negations has to be false. Yeah. So no 2 of them can be true at the same time. So you will have a bunch of conditions like this. In every row, every number appears and so on. Each of these conditions, if each of the rules of Sudoku, can be reasonably easily translated to a set of formulas with these Boolean variables. And now you have a list of conditions that have all have to be satisfied at the same time. And you will run the solver, and the solver will either tell you this is unsolvable, the Sudoku doesn't have a solution, or it will tell you here is one solution, a set of an assignment of truth values, and now you will go through all of the variables, and those ones that are true are telling you what number to put where in the Sudoku. So if you have a set solver, then you can solve anything. You can encode into these Boolean formulas. And a lot of research in the past decades has gone into perfecting the set solvers and coming up with new sets of tricks, new optimizations to make them work even faster. And yeah, so nowadays it's probably the most practical approach you can use. So this is not something you can use in most of the programming competitions, with some notable exceptions, but the ones where you submit your own code, then you cannot just submit somebody else's set solver. Usually there are rules against that. But if you actually in practice run into the need to solve a very big instance of a hard problem, like here's a graph and I want to find a Hamiltonian circle in it, then using a modern set solver is usually a much better bet than programming it on your own, because it's very unlikely that the optimizations you will be able to come up on your own for the specific problem you are solving will be better than what is already been done by several generations of researchers of perfecting these set solvers. And a very similar setting also exists when it comes to NP-hard optimization problems. For example, like traveling salesman, where you are trying to find the cheapest Hamiltonian circle in a weighted graph, visit all the vertices exactly once and come back when you started. There is again another type of solvers where you have what is called linear programming. This is an optimization technique that you can again take these optimization problems and write them as a set of linear equations and inequalities between some variables, and you can use this to model stuff that is also solvable efficiently, like maybe max flow, but you can also use this to encode all of these hard problems. And solving linear programs as such is easy. We can do this efficiently, but on real numbers. So if we can use real numbers, finding the optimal solution with real numbers assigned to the variables is easy. But you can also add the restriction that the numbers have to be integers. And in particular, you can again have 0, 1, so Boolean variables, whether or not something is used. And as soon as you have such variables, you can encode many more problems. And these problems become, again, they will include all of the NP-hard optimization problems. So all of them can be included, can be reduced to these integer linear programs. And again, we have solvers for this type of programs that have been optimized to do like all kinds of optimizations you can think of. And again, so yeah, I think the current state of the art, for example, for traveling salesman, if you really need to solve large practical instances, this will consist of two things. One of them is doing the reduction to the integer linear program in a specific clever way, and then using the best solver you can find. Yeah.
Are they always possible in binary time?
Yes, that's a very valid point. Actually, all of these reductions are like straightforward computations. So, for example, let me think about it for 30 seconds. So for example, again, if you have the traveling salesman, then the input is some kind of a weighted graph. And now what you can do during the reduction is you can say that for each of the edges, I will have a single variable that is either 0 or 1 that is telling me whether or not I'm using this particular edge. And now you need to make sure that what you get is actually a Hamiltonian cycle. And what you can do is you can start by, for each vertex of the graph, you can add a new constraint saying that the sum of these particular variables has to be exactly 2. So you will start with just having these n constraints, and then you can use the solver to find you the best solution it can. And the solver, sometimes on a bigger graph, what it will give you is, it will give you a set of edges that has the minimum possible sum, such that every vertex will have degree 2. So you may get something like this. Instead of the Hamiltonian cycle you wanted, you can have 2 triangles. And now it is also possible to encode the actual constraint of this being a Hamiltonian cycle into these kinds of, again, mathematical formulas. What you would do instead, you would use a slightly different set of variables if you wanted to encode it all at the same time. So you would have variables about your position in time. So you will have variables saying, am I in vertex k after L steps? And for these variables, you will then write the set of constraints. So if I'm in vertex k after L steps, then after L plus 1 steps, I have to be in exactly one of its neighbors and nowhere else. And for each vertex, the sum of the number of times I visited has to be exactly 1. So this will give you, again, a set of linear equations on these variables. And by solving such a program, you will directly get the actual cheapest Hamiltonian cycle. But this, what I started doing here, turns out to be much more efficient in practice. So you start with just the constraint that each vertex has to have sum 2, and this will give you the cheapest collection of cycles. And now each time you get a collection of cycles that is not a Hamiltonian cycle, what you can do is you can observe any cut in your graph. And in this particular solution, this cut remained unused. But in the optimal solution, this cut has to be used at least once and therefore at least twice. So you can add another constraint to your program saying that the sum of these edges must be greater than 0. And then you rerun the program. And you get another set of maybe disjoint cycles. And you repeat this until eventually you get a Hamiltonian cycle. And this has to be the cheapest one because all of the conditions are just necessary. They did not eliminate any Hamiltonian cycle. So as soon as you found one as the cheapest solution to your program, then you have it. All right. So these are some keywords to look for after the lecture. And if you are interested in stuff like this, SAT and ILP solvers. And in fact, in some of the rounds of the hashcode competition, when it was still running, this was a competition where we were supposed to do exactly this type of things, to do some, to find not the optimal solution because that's too hard, but to find the best solution you can, given the time you have for some specific instances. There was stuff like the transport problems and problems where we were plugging in routers inside the building and we were trying to cover it with the Wi-Fi signal as best as you could and so on. So for some of these optimization problems, we were actually able to use these type of ILP solvers, for example, to get some reasonable scores on some of the inputs. It's not always possible in these competition problems in hash code, but for some of them, this was a very good technique. All right, so now let's leave the one-player versions of games be, and let's go to two-player versions. And the stuff we'll start with are games with two specific properties. They are finite, and they are, I think symmetric is the proper word. Or maybe non-partial. Okay, I will explain what those mean. So a finite game is a game that has to terminate after a finite number of steps. That's a reasonable thing to ask from a game. Games that can go on forever and therefore like implicitly end in a draw can be harder to analyze and also much less pleasant to play. Usually you will die of old age before the game terminates. And the symmetry is the less trivial property. The symmetry means that in any position of the game, the set of moves only depends on so the set of moves is always the same, and you know the set of moves without having the information whose turn it is. So what this means is that, for example, tic-tac-toe and all various versions of that, gomoku and so on, where one of the players is playing X's and the other is playing O's, so or nodes and crosses or whatever you like to call it. This is not a symmetric game, because if you see a position of the game, then if it's the O player's turn, then the valid moves are placing O's into the empty positions. And if it is X player's turn, the valid moves are playing X's. So the next move of the O player will create different boards than the next move of the X player. Also, for example, chess is a game that is not symmetric because one of the players is playing with white pieces, the other player is playing with black pieces. So these are not symmetric games. It's just finite. Yes is correct, no is also correct for different different meanings of the question. So on its own, with this just standard set of rules, chess is obviously not finite because both players can take their knight and jump the knight back and forth. Tournament chess is finite because tournament chess has extra rules that are saying stuff like if the position is same position repeats 3 times, the game is over. As a draw, this would already be enough because there is only a finite, even though very, very large, but a finite number of positions, and therefore eventually either you have to get a checkmate or a position has to repeat 3 times. So the game tree becomes finite by just adding this rule. There is also a second rule about something like 50 moves without moving a pawn, and that can also be used to claim a draw. So tournament chess is finite, standard chess, casual, non-ranked, non-competitive chess is not finite. Okay, so what is a symmetric game? What does a symmetric game look like? A very easy game is the game NIM3. NIM is a whole class of these symmetric games. It comes from the German word for to take. And these are games in which the players take some objects away until one of them is not able to do a move. And for this very simple game that I will use as a very quick example of what's going on, the rules are as follows. You have a single pile of n objects, and whenever it's your turn, you can remove up to 3 of those objects from the pile, and whoever doesn't have a valid move loses the game. This is the most standard rule in all of these types of games. If it's your turn and you cannot make a valid move, this means that you lost the game. This is in fact so common that it is formally mathematically known as the normal play of the game. So, analysis of such a game. This is something probably most of you have already encountered. Again, we can view the game as a state space. So, the entire description of a state is just a single number. How many objects are still on the pile? And the final state, there is exactly one final state. When the pile is empty, there are 0 objects. If you are in this position and it's your turn, you have just lost the game because you don't have any valid moves. If there is 1 object on the pile, you have exactly one option what to do. You take the object, and then your opponent loses the game. If you have 2 objects on the pile, you could take one of them, or you could take both of them. And clearly, the optimal move is to take both of them, and you win the game. If you take just one, then your opponent takes the other one, and you lose. If you have 3 objects on the pile, you can take 1, you can take 2, you can take all 3. If you have 4 objects, you can take 1 of them, 2 of them, or 3 of them, but you can not take all 4 because these are the rules. So you can visualize the entire state space of the game as this type of a graph. And now it should be obvious that we can classify these positions into 2 types. There are positions where if it's your turn to play the game and both players play optimally, then you are guaranteed to win the game. You have a winning strategy. There is a good move you can make, and the move guarantees you that you win the game if you follow the optimal strategy for the rest of the game. And there are losing positions. If you are in this position and your opponent plays optimally, regardless of what you do, you will lose the game. And we can label these positions starting from the very bottom. So position 0 is losing by default. There is nothing you can do. You lose immediately. Positions 1, 2, and 3 are clearly winning. Why? Because from each of them, you have a move into position 0. If you are in position 1, 2, or 3, you can win by removing all of the objects. Why do you win? Because this particular move places your opponent into a losing position. What about position 4? If you are in position 4, regardless of which move you choose, you are placing your opponent into a winning position for them. And if you are forced to put your opponent into a winning position, then your position has to be losing. And now, for any finite game, what it means that the game is finite is that for any starting position, if you take the state space of all of the reachable positions from the starting position, you will get a finite graph. Finite directed acyclic graph. You cannot have cycles because a cycle would be corresponding to playing the game forever by making moves that go through the cycle and states of the game are repeated. So if the game is supposed to be finite, the underlying graph has to be acyclic. There can be no cycles. And if there are no cycles, then from the bottom to the top of the graph, you can always propagate this information about the graph. So this gives us, for any such game of 2 players, a very straightforward option how to analyze such a game, at least for small starting positions. So we can have a recursive function whether state is winning, and what you do for each possible move. If the next state you will get from the current state by applying this particular move. If you have a move that will get your opponent into a losing state, then your state is winning. And if you went through all of the possible moves, and each of the moves gives your opponent a winning state, then your state is losing. So you can do this for any game. And if you just run this recursive function, what it will do is it will use backtracking to explore all possible ways in which the game can be played, and eventually determine whether the positions are winning or losing. Well, it doesn't have to explore all of them because it's returning early in some cases, so some parts of the game tree will not be explored, but it can still be worst case exponential. But there is obviously the second step you can do in all of these games. You can realize that the answer to any particular question, whether this particular state is winning or losing, the answer doesn't change in time. As soon as you have computed this answer once, you know this answer, and the answer will remain the same each time you encounter the same state in the future. So what you can do in Python is you can just do the decorator that does memoization, or in any other programming language you can do memoization, or you can do, if you prefer, dynamic programming. So you can do sorting of the states on your own by hand, so you can identify what is the smallest state, what is the state at the end of the game, in which direction the states grow, and then if you process them in this particular order, when you are processing a state, you already know the answers for all the reachable states, and you can directly compute the value stored. So if you apply memoization to the recursive function, or if you do DP from bottom to top, from the smallest, easiest states to the original starting one, then you will process each of the states exactly once. So this gives you, for any two-player finite symmetric game, this gives you the baseline solution. This is something you can do, and you can solve the game for small inputs. And once you can do this, now comes the creativity part. Because we can ask the question about very large states of the game. What happens if there are 10 to the 18 stones on the pile? If there are 10 to the 18 stones, you don't want to traverse this entire path and try to process each and every value between 0 and 10 to the 18. You want to come up with something more clever. So we can start thinking about, again, reducing the state space, finding symmetries that can make us merge states into one, or finding patterns. And in this particular case, it's very, very easy to observe the pattern, because now position 4 is losing, position 5, 6, and 7 are winning, because from them you can move to position 4 and put your opponent into a losing position again. Position 8 has to be losing, because from 8 you can go only to 5, 6, and 7, and those are winning, and so on. And it's very easy to observe that the multiples of 4 are the losing positions, and everything else are the winning positions. And now that we have made this observation, we want to prove this. And here's a little trick I do when I have to write down a proof like this one. In order to not get confused between what is this I am claiming, what I'm trying to prove, and what I already have shown, I will mentally assign two different colors to the positions. So I will say that there are blue positions, and there are red positions. So blue are multiples of 4, and red is the complement of it, everything else, all the natural numbers that are not blue. And now the claim is that blue positions are the losing ones, and the red positions are the winning ones. I can't write. Yeah. When writing on the whiteboard, you can see that sometimes my brain is going faster than my hand, so I skip letters when writing. I don't know whether it happens to you as well, but I had this for years, and I just got used to it that, yeah, I can't delete it, otherwise like going back and erasing. So this is what we are trying to prove. And how do you prove this? So you need to show that those two or three properties are satisfied. So here are the blue positions, here are the red positions, and you need to show that for any position that you are claiming to be winning, so for any red position, there is at least one move that goes to a blue position. There can be others, but there has to be at least one move that gets you to a blue position. And for any blue position, you have to show that all possible moves put you in a red position. In particular, it is also possible that there is a vertex in the blue positions that has no outgoing edges, no possible moves, And for this one, this is vacuously true. So if there are no moves, then yes, it is correct that all possible moves lead to red positions. That one is fine. So these are the two things you need to show. And as soon as you show these two things about them, then it is implied that you have to be correct and this has to be true, that blue have to be exactly the losing ones and red to be exactly the winning ones, because essentially you can the final step of the proof is just mathematical induction. All of the final states, the ones where the game is over, have to be in the blue set. And now you are exactly applying the definition of winning and losing positions. If there is a move from a position to a losing one, then this one is winning. So if you already know about this position that is losing, then inductively this one has to be winning. And if you already know about all of these that they are winning, then this position has to be losing, because regardless of what you do, you are putting your opponent into a winning position. So if you show these two things about your sets, then you have won. You have showed that the blue ones are losing, the red ones are winning. What happens in our game, if you have a position for n, then there are either no possible moves if n is 0, or there are exactly 3 possible moves to 4n minus 1, minus 2, and minus 3. And all of these are red. So for any blue position, all of the moves go into red positions. And for any red positions, if you have 4n plus r, and the r is somewhere between 1 and 3, then among the 3 possible moves, one of them goes to exactly 4n by removing r. So for any blue position, you are forced to put your opponent into a red position. For any red position, you have at least one way of putting your opponent in a blue position. And therefore, blue are losing, red are winning, and we have a solution for the game. So if you are given the starting value, starting number of tokens on the pile, then you can just look at the modulo 4 and you know the answer. Again, one story to highlight how important it is to make sure that you know all the rules of the game before analyzing it. Instead of NIM3, there is also the general game of NIM. And for a single pile, so instead of NIM3, you can have other versions where you are somehow restricting the set of moves that are possible. So for example, you can ask the questions, if in every move the number of tokens I remove has to be a prime number, what is the optimal strategy? What is the classification of positions for winning and losing? What if it is a multiple of 7 plus 3 only, or whatever? You can use any kinds of different restrictions, but you can also have a version of this game that is completely unrestricted. So at the beginning there is a single pile with n items, and when it's your turn you can take as many of them as you like. On paper this is a very boring game, right? The optimal strategy is if you start with 0 tokens, then you have already lost. And if you start with a positive number of tokens, then the winning move, exactly one winning move, is take all of them and then your opponent lost. So during one of the programming camps we did in Slovakia back in the day, this was for like high school kids, ages between 15 and 18. We told them that yes, you are going to play this mathematical game. Come to the classroom, we will explain the set of rules, and then we will go outside and play the game. We set them down in the classroom and we told them, like with very straight faces, we explained the rules to this particular NIM game. So there are 2 players, they take alternating turns, there are n objects on the pile. Whenever it's your turn in a single move, you can pick up as many of them as you like and remove them from the pile. And whoever doesn't have a valid move loses, so whoever takes the last stones from the pile wins the game. So they had a laugh that, yeah, this doesn't make sense, this is very obvious that the first player wins immediately, why would you want us to play this game? And then, as we promised, we went outside, and when we went outside, we have prepared piles of actual stones. So there's a pile of stones like this, and suddenly the rule, the exact wording of the rule, when it's your turn, in a single move you can remove as many of them as you can, started to matter. So that the game turned from actual free-for-all NIM to you have to judge whether you are leaving enough stones for them not to be able to remove all of them in a single move. And it actually turned out to be a pretty fun game to play. So again, making sure that we understand the rules is important. Okay, we are getting pretty close to the coffee break, so before we do the coffee break, let me talk about one more game and show you one more concept that will be like a very introductory concept what you can do in these games. And this will be one of my favorite games ever. It's very simple. It's a game called Daisy. And it's played with an actual flower. So you can play it when you pick up a flower somewhere on the meadow. And what you need is a flower that has on the center a sequence of petals that goes around the center in a single circle. So there is a linear ordering of those petals. And now with such a flower you can play a two-player game. And in order to play the game when it's your turn, you can either remove a single petal from the flower, or you can remove two consecutive petals. And these have to be petals that have been consecutive on the original flower. So if you have a gap like this, now it is not possible to remove these two because they are not consecutive. And again, this is a game between two players. They take alternating turns. Whoever takes the last petal wins. So equivalently, whoever doesn't have a valid move loses the game. And now, this is a much less obvious game to analyze than the NIM3 game. For this one, it probably will take you a bit of thinking about it. But we can start with very simple observations again. So if you don't have any petals left, it's by definition a losing position. If you have a single petal, it is a winning position. Take it and place your opponent in a losing position. If you have two adjacent petals, again, you could take just one of them and move here, but then your opponent would win. A better strategy is to take both of them and place your opponent into a losing position. But now there is also another configuration with two petals, where the two petals are not adjacent. And this is a losing position because we can only remove one of them, and regardless of which one we remove, by symmetry we are moving our opponent to this position. So we take one, the opponent takes this other, and we have lost. So right now, if we have Daisy with n petals, and we just do this straightforward search through entire space, there are 2 to the n intermediate states we can encounter. Because generally it is possible to reach each and every combination of still present and missing petals around the daisy. So the brute force, so even if you do memorization or dynamic programming, when you are labeling the states as winning and losing, you are limited to n being somewhere around 25 or maybe 30 if you try really hard. Like 2 to the 30, you just need to store 1 bit per position, so it should still be able to squeeze into memory. But beyond 30, it's hard to get. And so brute force doesn't really help us win this game. What does help us win this game is a new concept I will introduce now, and this is symmetry. Symmetry not in the sense of game moves, but this time symmetry in the sense of a specific position of the game. And I will give you a full strategy for the game, and the strategy will look as follows. So suppose you have a daisy with more than 2 petals, because we already analyzed the small ones and we know what happens there. Now the first player takes their turn, and doesn't really matter what the first player does. They can, somewhere on the daisy, they can remove 1 or 2 petals. And essentially what they just did is, instead of having a circle of petals, we now have a line of petals. So this configuration is now mathematically equivalent to having a configuration like this. So instead of having petals around the center, we can just imagine them arranged in a row. And now the only thing that matters is the parity of the length of this row. So in my example, it's 4, 5, 6, 7, 8, 9, 10, so it's even. So what I do now is I eat from the middle of the row, and I eat either 1 or 2 petals in such a way that after the move, I'm left with 2 equal parts. And what does this mean for the rest of the game? So, player 1 did anything they liked. Afterwards, player 2 can always choose either 1 or 2, depending on the parity of the length, so that they create the situations like this. And once player 2 does this in their first move of the game, they have already won. Or more precisely, they already have a very clear winning strategy. And what is the winning strategy? It is simply mirroring the first player's moves. So if the first player does something on the left side, we do exactly the same thing on the right side. If the first player does something on the right side, we do then exactly the same thing on the left side. And now there are two separate observations that together mean that the player 2 has to win. First, the game is finite, the game eventually has to end, and somebody has to be the one who runs out of moves and loses. But on the other hand, player 2 can always guarantee to be able to make the next move, because whatever player 1 did, they can mirror. They always have the option to do the same thing in the other half of the game. So by creating a symmetric position, a position consisting of two equal parts, player 2 now has this valid strategy of mirroring player 1's moves, and this is a strategy that can always be applied. So player 2 is always guaranteed to have a move, the game is guaranteed to eventually end, and therefore the unlucky person who loses the game has to be player 1 eventually, regardless of what they do. So symmetry is a very powerful tool we can have in analyzing games like this one and finding strategies for these games. And this doesn't necessarily only apply to full positions of the games. So right now we can already see that we can encode the positions of the game with the daisy as not just a single number, but the sequences of numbers. This is a good way of encoding the positions and giving us the information. So as soon as this player removed this original petal, we got the position 10. So there is a single strip of length 10. And from this position, the second player created the position 4 and 4. There are two separate strips, each of length 4. And now if you take, for example, this cell, then the new position is 1, 2, and 4. Here are the 1, 2, here is still the 4, and now we break this 4 by doing exactly the same thing, and now we have position 1, 2, 1, 2, and this is again symmetric. There is left, there is right, there is still twice the same. So for example, suppose you have a position that looks like follows: 12, 17, 13, one more 17 here, and one more 12 here. So you have these 5 blocks of petals. Is this a winning position? Is this a losing position? And if it is winning, what is the winning move? It's winning?
Split the 13 into two sixes.
Yes. So you take the 13, you remove the middle petal from that one, and you create 2 sixes out of it. And now you can divide these mentally into 2 blocks. You can have 17, 12, and 6, and you can have 17, 12, and 6, and these are your 2 halves. You have just made the position symmetric, and from this point on, you can apply the symmetric strategy to win the game. So this was a winning position. So what we just did is, using this very simple trick, we can win. We know that for what happens is that for any n greater than 2, so for n equals 1 and equals 2, these are very trivial small cases when the first player can take everything and win. From n equals 3 on, the second player has always this symmetric strategy. So starting from a full daisy, we have analyzed the game for any n. We know what happens. We can use the symmetry observation to solve some of the more trickier positions. But what we still cannot do efficiently, only using the brute force algorithm that explores all possible gameplays, or all reachable states at least, what we cannot do is solve general positions. So if I give you a general position on a daisy where you have segments of length 3, 7, 13, and 25, at the moment we have no idea how to solve this efficiently, how to just look at these numbers and tell who is winning, who is losing. We will get there, but we will get there only after the coffee break, which I believe now is the appropriate time to do it. So after coffee break, we will explore the theory that will get us to this solution. the coffee break, so we'll take 1 more minute for everything to settle down, and then we can continue with the lecture. Okay, so to start, one terminology correction, and I was struggling to remember the proper English word for names where it doesn't, the information whose turn it is doesn't change the set of valid moves. The proper name in English is impartial from the games like this. And just to confuse matters further, you don't use partial as the opposite. You use partisan as the opposite of impartial in this particular terminology. So, yeah. None of the languages always make sense. And this is one of those cases. So impartial is what I should have used for the symmetric games as terminology. Okay, so where we left off before the break is we want to find out how to solve the general version of the Daisy game. And it turns out that when we learn the proper technique that can be used to solve this, it can actually be used to solve, or it is applicable to all of these finite impartial games of all types of shapes and sizes again. So it will be very useful. And we will start by returning to the general game of NIM. And you can remember that this was the very simple game where you have a single pile, let's say with A objects. And when it's your turn, you can remove as many of them as you like. And this particular version of the game is pretty boring because you either lose directly or you take everything and your opponent loses directly. But the situation starts to be more interesting if we had multiple piles. So if you have 2 separate piles of tokens and there is A tokens on one of them and B on the other, and the rule remains the same. If it's your turn, you have to choose just one of those piles and then remove some tokens from the pile. Then you can take as many as you like. You need to take at least one. You can take as many you like, up to all of them. What is the winning strategy for this particular game? What is the classification of positions into winning and losing ones? Yeah, so the claim is A equals B are losing positions, and A doesn't equal B are winning. Why is this so? Again, when we want to show this, we need to show that if you are in a losing position, you must move your opponent into a winning position. This is clear. Because if both piles are the same, you have to choose one, remove something from it, and now they will no longer be equal. And if they are not equal, you can always... So for this way, all of the moves have this property. And in this direction, there exists a move with this property. And what is the move? If you have a bigger pile and a smaller pile, then you choose the bigger pile and you remove from it as much as you have to make both piles equal again. And you can notice that this is exactly the symmetry strategy we were discussing before. If there is a symmetric situation, 2 piles of exactly the same size, then the player whose turn it is loses. This is the same we had with the Daisy, because whatever the player does with one of the piles, his opponent can do exactly the same thing with the other pile. And this will maintain the invariant that after the winning player move, both piles are the same. And regardless of what you do with one of them, I can always do the same thing with the other, and I will always win. So we can use symmetry to solve this game. And the game becomes interesting as soon as we add pile number 3 with C tokens. And this is probably the most interesting result of the entire combinatorial game theory. The result itself is now over 100 years old. So in the very early 19th century, this was already analyzed, if I remember correctly. What is the winning strategy for the general position in this game? And it turns out that for this 3-pile version of NIM, the classification of positions is no longer so clear. So what you can do when you are given a game and you suppose you don't know the answer yet, one of the things you can do is you can try analyzing the small positions of this game by simply implementing the brute force solution, so recursive search and possibly with memoization, and just listing either all of the winning positions or all of the losing positions, or like printing out the table and trying to see a pattern, trying to guess what's going on, and then formulate the guess as a theory, and then try to prove that your theory is correct. This is a natural way how to analyze games like this one. One thing you may notice with this particular type of game is that almost all positions will be winning. Only a few of them will be losing. Why is this the case? Well, if you have a losing position, A, B, and C, if this is losing position, belongs to the set of all losing positions, then what happens with positions, let's say A, B, C plus 17? So if you change just one of those numbers, the position can no longer be, if you make it bigger, you no longer have a losing position, because from this position you have a move there by removing those extra 17. So all of the positions that differ by just making one of those piles bigger will automatically be winning. So if you imagine like the state space here, you can visualize it like three-dimensional space. So you can have a cube and divide it into little boxes, and each of those boxes is one of the starting positions. And if you label one of them as losing, then everything that follows in the row, column, and vertically as well will be winning positions from there on. So each one losing position will give you many winning positions in the rest of the box. So the losing positions are the infrequent ones. And when you start printing those and looking at them, then you will see some of the familiar ones, like you will see a position 7, 0, 7, because this is just the two pile situation. So this is the same as you had 7, 7. The 0 pile can be ignored. So this is a losing position. You will then see losing positions like 1, 2, and 3. And for this one, you can verify it by brute force what happens in all possible gameplays. If you are in the position 1, 2, 3, then you will lose if your opponent plays optimally. And you will also see a position 2, 4, 6, and all of permutations thereof. And you will start to formulate, maybe there is a theory that like, maybe if sum of two of the piles is equal to the third one, then it's losing. But 1, 5, 6 is winning. And then you will encounter also situations like 4, 5, and 6. And I think, is this a losing position? No. No, but I want the 5 and the 6, and what's the next? Then is there 3? Yeah. I think this should be a losing position. And here none of them are the sum of the others. So what is exactly going on? And if we list up more of the losing positions, we can come up with a very surprising theory that the losing positions seem to be those where the bitwise XOR is 0. So exclusive OR or XOR is the operation in binary where you put those two numbers underneath each other. And the XOR is like addition modulo 2, but you are not carrying over the carry. You are just processing each pair of numbers separately. So exclusive OR of 0 and 1, or 1 and 0 is 1, and 2 zeros and 2 1s give you a 0. In other words, XOR is the same as parity. And you can do this, so it's commutative, it's associative, so we can do this with all of the numbers at the same time. So what we are saying is that if you write down all of the numbers, all of the pile sizes in binary, then each column has to contain an even number of ones. And if this happens, this is a losing position, and if this doesn't happen, this is a winning position. Okay, in a moment we will show why this is the case, but let's now take a short break and appreciate how crazy this is, that this is the pattern that appears. So there is literally nothing in the rules of the game that has anything to do with binary, right? There's no reason at all why the binary representations of the pile sizes should have anything to do with the position being winning or losing. The rules are very simple. It's just 3 piles of tokens. When it's your turn, choose a non-empty pile, remove as many tokens as you like. And it's very, very surprising. And appreciating this surprise is quite a good thing to do before we actually look at the proof why this is the case. So let's now show a proof of this pretty surprising result. So we have again 2 types of positions. We have blue positions, which are those triplets A, B, and C, such that their bitwise XOR is exactly 0, and we have red positions that are all of the other positions. So where the bitwise XOR is non-zero. And now the claim is that the blue positions are exactly the losing ones, the red positions are exactly the winning ones. So what we need to show is we have the blue positions, we have the red positions, and for each position here, we have to show that all of the moves put us in the opposite color, and for each position here, we need to show that there exists a move that will put us into the opposite color. One direction is pretty easy. That's this one. So we have a position where the bitwise XOR is exactly 0. So we have the number A written in binary. It can look something like this. We have the number B written in binary. And we have the number C written in binary. And in every column, as the bitwise XOR is exactly 0, in every column we have to have an even number of ones. So if I know what A is, and if I know what B is, the value of C is exactly determined by those two. There's exactly one such C that will make the XOR come up exactly to 0. And what it is, in this column we need an even number of ones, so we need a 1. In this column we need an even number of ones. Let's make this a 0. So here there will be a 1, there will be a 0, a 1 again, a 0 again, and the 1 again. And this is symmetric, so if I now cover the B, if I erase the B, you can reconstruct the B from seeing A and C again. For each position, you know whether there has to be a 0 or a 1 to get the XOR exactly equal to 0. So if you now do the bitwise XOR, in each column you have an even number of ones, so the result will be all zeros. And now, what we need to observe for this direction, if you have such a position where the XOR is exactly 0, and you make any valid move, what happens is that this valid move will change exactly one of the piles. So one of these numbers will change into a smaller one, and therefore the XOR cannot remain 0 because there is this unique number that worked, that made the XOR 0. As soon as you change exactly one of those numbers, the XOR cannot remain 0 because you changed it from the one that worked into another one that definitely doesn't work. So this is the easy direction. If the current bitwise XOR of the pile sizes is 0 and it's your turn, regardless of what you do, you have to violate this condition. You cannot make a valid move and have the XOR remain at 0. And now comes the trickier part, and that is this. Why is this trickier? Because, well, you could argue that, okay, when the XOR is non-zero, I can choose any of the piles, and I can then compute what is the number that should be there, and I can change the number that is there to the number that should be there. Why is not this a complete proof?
Because you're assuming that you can go to every other number.
Yes, exactly. So the problem is that the new number, the number I need, can generally be higher than the number I have. And in the game of NIM, I cannot add new tokens, I can only remove. So what I need to show is I can always make a valid move that will decrease one of those numbers and thereby produce XOR being 0. And I can show this on an example, what the strategy is. So suppose you have, again, 3 numbers, and now their XOR is non-zero. So here's an example of what it can look like. Here we can have two ones. Here we can have 2 ones and the 0. Here we can have all 0 column. And now, let's say, here we have a column with 3 ones. And now, there is the rest of the numbers. So if the XOR is non-zero, you can go from the left to the right. And eventually, after seeing a few columns that will have XOR 0, you have to hit a column where the XOR is 1. In our example case, it's this column. And this column has an odd number of 1s. And it turns out that the rows that have 1s in this column correspond precisely to the winning moves we can make. We can choose any one in this column, and as their number is odd, there is at least 1. So let's say we choose this one. So how do we make a valid move? It's very easy. What you do is this particular one will change into a 0. And for the rest of the row, you simply go column by column and you compute the bits you need there. So here we already have an even number of ones, so we put a 0. Here we have an even number of ones, so we put a 0. Here we need a 1, and here we needed 1 as well. And this gave us a valid move in the game. Why was it a valid move? Because it is guaranteed that together all of these operations decreased the number. Why is this the case? Because this is the highest bit that changed, and this one changed from a 1 to a 0. And regardless of what we did with the rest of the number, the new value has to be smaller than the original value. So any one in this column, the first column that breaks the XOR being 0, any one can be changed to a 0, and the rest of the row can be then set to the appropriate bits. So this is why there always exists a winning move in the game of NIM. Yes? Yes, so suppose you have some specific pile sizes. I will now not bother converting these to binary, but let's say it's something like 175, and this one should be 131, I think, or something like that. And this one should be 150. So you have these three specific pile sizes. You know that their bitwise XOR is not equal to 0, and you want to find a winning move in the game. What you do is you first write the numbers in binary, aligning them on the right side, so the same bits are below each other. And now you are going to find the winning move. And how do you want to do? How are you going to do this? So currently the XOR is non-zero, and you want to make it 0. So you need to do this by decreasing one of the numbers. So you need to choose which number to decrease, and you do it by going through column by column. And this column, if you look at the XOR, this is 1, 1, 0. The XOR is 0. Everything's all right. This column as well, they have XOR 0. And in the original numbers we had, this column had 3 1s, so the XOR here is 1. So this is the first place we have to fix. Everything that's on the left we can leave as is. This is the place we need to fix. And the way we will fix it, we will choose any row that has a 1. And if the XOR is 1, we have to have such a row. I did choose the middle one, but I could, in this case, I could choose any of the 3 rows. And then you can decrease the original number, which was 1001 and something afterwards, into 1000. And then you fill the rest of the row in order to just make all of the columns XOR to 0. So this one now has an even number of 1s, this one has an even number of 1s, and so on. And this is always uniquely doable. So for any row that has a 1 in this first column where there is a conflict, you can make a valid move by changing the 1 to a 0 and then fixing the rest of the row exactly to one specific pattern of 1s and 0s that will produce XOR 0. And now you can look at the new value of this number. So originally this was, let's say, 147, and now the new value is 131. So your move, the winning move we just computed, is choosing this pile and removing 16 or whatever tokens. Okay. Now, at least we can now make some generalizations that are pretty easy. First of all, we can notice that this solution works not just for 3 piles, it also works for 2 piles, because for 2 numbers, the XOR is 0 if they are the same, and the XOR is non-zero if they are different. It also works for a single pile, because for a single number, the XOR is 0 if it's 0, and is non-zero if it's just if it's positive. So this particular pattern works for 1 pile, 2 piles, 3 piles, and it's no longer a surprise that it actually generalizes also to more piles. So regardless of how many piles you have in the game of NIM, if you are still playing the same game, so all piles are independent when it's your turn, choose a non-empty pile, remove as many tokens from the pile as you like. If you do this, then for any number of piles, the strategy is always the same in order to classify positions as winning and losing. Losing positions are those where the bitwise XOR of all of the pile sizes is exactly 0. Winning positions are all of the remaining ones. And it turns out to be the case that this surprising pattern appears not just in the game of NIM, but it appears throughout all of the combinatorial games we have. And soon we will see why this is the case. Before we get to the more general observations, let's look at another game that is not even finite, or at least seems to be so from the original statement. This is a game by a guy named Northcott. And Northcott's game looks as follows. We have a rectangular board. And in each row of the board, each row is kind of separate. And in each row of the board, there is a black token and a white token. They can sometimes be next to each other. They can sometimes have swapped places. So the white one can be to the left of the black one or to the right. And so on. So in each row, there is exactly one black, exactly one white token. And now this is a game that is not even finite, and it's not even impartial. So in this game, there is a black player and there is a white player. And when each player has their own tokens, and these are the only tokens they can touch. So when it's your turn, you can choose any single one of your tokens, and within the row, you can slide the token. You have to move it, and you can move it left or right, as many squares as you like, but you cannot touch or cross the position of the other token. So if you choose this white token, you have 4 options. You can move it there, 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 or there. In some cases, you can have a token you currently cannot choose. So it's if you are white and this is your turn, you cannot choose this token because this one is currently squeezed to the edge and doesn't have any valid moves. So you have to choose any one of the other tokens. And for this game, again, the questions are the same as always. So the setting is normal play. If you are unable to make a move, then you lose. And the question is, analyze all the positions of this game. Tell me what's the winning strategy. Tell me in some position who is winning, who is losing, or whether there maybe are positions where the game will go on forever. So neither player has a winning strategy, but neither player can also wants to end the game, and each player has a way of playing the game forever. It can theoretically be possible. So what happens exactly in this particular game? Wow. And yeah, I will give you the solution because discovering it completely can take quite some time. But first of all, I will ask you a simpler question, and this one you should be able to answer. What would the outcome of the game be if instead of sliding the tokens in any direction, the rule was such that you have to slide the tokens only towards each other? So when it's your turn, you have to choose a token of your color, and you have to slide it at least one step towards the opponent's token in the same row. What would the answer be then? It's a name, yes. What are the pile sizes?
The distance between the tokens.
Yeah, exactly. So the distances between the tokens can then exactly be seen as the pile sizes in the game of NIM. So these ones are already next to each other. They are no more possible. This is essentially a pile of size 0. This would be a pile of size 2. So when it's your turn, you can do 1 step towards the enemy or 2 steps towards the enemy. And that's exactly what you could do in the game of NIM. So like from 2, you can go down to 1 or down to 0 with the distance. And the same in each other row. So this one would be a pile of size 6. When it's your turn, you can decrease the 6 to any smaller number you like and leave it there. So you can move it to 5, to 4, and so on. So the answer for this game would be that you look at the distances, you compute their bitwise XOR, and then it will tell you for whom it is a winning position. And then the player with the winning position can play exactly the same strategy as in the standard game of NIM. So you look at the pile sizes, you find the one where decreasing it just right will change the bitwise XOR to exactly 0, and you make that particular move with your token. Okay, so the easier version of the game we could solve. What changes if we allow the moves in the other direction? And this is the main reason why I'm showing you the game, because now you need to make the observation that the moves in the opposite direction don't really change anything. So the only thing they can do is they can delay the inevitable, let's call it, by a few more steps. But eventually, the player who could win in the game where we are just able to squeeze them more together will still win the game. So let's do the same argument more formally one more time. So suppose that, as before, we look at all of the distances, we compute their bitwise XOR, and suppose it is non-zero. So in the original game of NIM, it would be a winning position for us if it's our turn. And now what we can decide to do is that we can decide that regardless of what the opponent does, we are playing NIM. We will always make the winning move in the game of NIM, and this will eventually give us the victory. So why is this the case? So currently the XOR is non-zero. We will make a move closer toward one of the opponent's pieces. That will make the XOR exactly 0. And now, regardless of what the opponent does, now the XOR of all of the distances is 0. If the opponent makes a move, regardless in what row, and regardless of whether they increase or decrease the distance, they are changing exactly one of those distances. Either they agree to play the game of NIM, in which case they also decrease one of the distances, and we just made 2 steps of the game of NIM consecutively, or they move it away from us, they increase one of the pile size, but still what the effect is that the XOR was exactly 0. They changed exactly one of those values, so now the XOR is non-zero. And one of the options we now have, so now we are again in a winning position in the game of NIM, and in particular one of the winning moves we have is in the same row where the opponent made the move away from us. We can replicate the exact same move, and this will bring the distance same to what it was before. So now we are still winning in the game of NIM. We made the XOR exactly 0, and the opponent's piece is now closer to the edge than it was before. So they spend the move on like removing some leeway from the game, but that's all that they achieved. The XOR is 0, the set of distances is exactly the same, and they are just closer to the edge in this particular row. So they can only do this infinitely many times, so in each row they have some buffer on the side behind their token where they can retreat, but they can only do this finitely many times, and then all of their tokens are already on the edge, and they are forced to do a valid move in the game of NIM. So eventually, after finitely many steps, we will still win the game of NIM. And we don't even have to do this consideration like specifically in our program, like if they retreated, then move in the same row. It doesn't matter. We are moving one of our tokens towards theirs, so we are pushing them closer and closer to the edge of the board in this particular row. And yeah, this will eventually give us the win. So we can just play NIM. We can disregard all of the other existing moves. We can disregard the option that our opponent can retreat. So if we are playing the game of NIM, if we just in each and every iteration when it's our turn, the XOR is non-zero, we find a valid move in a game of NIM where we are going closer to the opponent's token, and we make the XOR exactly 0. And first of all, this guarantees we will never lose, because after the opponent's move, the opponent is in a position when the XOR is 0. They have to make a move, and if they cannot, they lose. If they can, they will put us in a position where the XOR is again non-zero, and the XOR being non-zero means that there is still a move to be made. So we can never lose. And if we take a look at the specific metric, so for each of our tokens, we can compute the distance not to the enemy token, but to the end of the board behind the enemy token. And in each step of the game, when we are just playing NIM, we are pushing one of our tokens closer to that edge of the board. So the sum is always decreasing, and this guarantees that the game will be finite. So even if the opponent sometimes chooses to retreat, after finitely many steps, we are guaranteed to win the game. So the main observations about this is that this kind of resembled the game of NIM, and even though the losing player has the option to make some other moves in addition to playing NIM, those moves didn't help them. And even though the winning player also had the option to make some other moves, the winning player didn't need those moves. So the winning player could just say, I'm playing NIM, and that's it, and win by playing NIM. And the other player had some other options, but they were such that they didn't help them. So they were essentially forced to play NIM and lose. And this is the kind of pattern that happens in the combinatorial games in general. Many of the combinatorial games, in some sense, resemble the game of NIM. And when we can find the similarity, then we can usually show that even though there are also other moves possible in these games, for one of the players, they don't help. For the losing one, and for the winning player, they are not needed. And this is the mathematical intuition behind the results I'm going to show you now. And this is kind of the main hammer of analyzing normal plane combinatorial game theory. And this is a result that was independently discovered by two gentlemen. One of them is called Sprague, and the other is called Grandi. And they came with a novel way of labeling positions in a game. And using this particular labeling, we can then analyze what is called sums of games very efficiently. So let me show you first of all how the numbering works, and then I will explain how it can be used to analyze games. So initially, what we were doing is we were doing this very simple analysis where a position that was at the end of the game that had no outgoing edges was losing, and then for any other position you had one bit of information. So if there exists a move into a losing position, your position is winning. And if all of your moves lead to winning positions, then your position is losing again. So for each and every state of the game, we are computing just a single bit of information. And the trick these gentlemen came up with is just a pure generalization of this observation. And the generalization works as follows. So if you have a state S, and you have a valid moves to some new states T1 through Tk, what we are going to do now is we are not going to just assign Boolean labels, so there will be not just true or false, winning, losing, but now each position will get a number, a non-negative integer number. And the numbers are defined as follows. So the Sprague and Grandi value of this particular state S is what is called the minimum excluded value of the set S, Sg of T1, Sg of T2, and so on, Sg of Tk. So in human words, what you do is you look at all of the possible moves from your current position, from your current state. You get some new positions. And if you already know the value of each of these positions, and the values are, let's say, 0, 1, 3, 7, 0, 14, and 2, what you do is you look for the smallest value that does not appear on this list. So there is a 0, there is a 1, there is a 2, there is a 3, but there is no 4. And the smallest value that does not appear on this list is given as the number of this particular state. Okay, so first bit of intuition. I was saying that this definition is a generalization of just having a winning and losing positions. Why is it a generalization? Yes, exactly. Losing positions are precisely the ones that get a 0. And again, we can prove this by induction. If you are in the terminal position where there are no more moves possible, there are no more moves possible. So the set of reachable values is empty, and the smallest value that doesn't appear in an empty set is a 0. Now this position can only go to a 0, so it would get the number 1. This position can go to a 0 and a 1, so it will get a number 2. But in general, if there exists a move that puts you into a 0 position, then you see the 0 within the set of reachable numbers, and your number will therefore be non-zero. And on the opposite side, if all of the states you can reach have non-zero values, then your value will be 0 because you cannot reach a 0. 0 is the smallest number you cannot reach. And we can now inductively along the graph prove that zeros will be exactly the losing positions and positive values will be the winning positions. And like to give you a bit more intuition, what these numbers are telling you is that in some sense, this particular state of this particular game, and we don't care what game it is, we just view it as a state graph, we don't care about the rules. So regardless of what game it is, this particular state of this particular game is behaving kinda like a NIM position with exactly 4 tokens. Yes, because if you have 4 tokens in a game of NIM, you have the option to removing 1 and making them 3 tokens, you have the option of making them just decreasing the size to 2, to 1, or to 0. And if you have all of these options, then from this state, you can play the game as if it were a game of NIM with 4 tokens. There can be also other moves possible, but eventually it will turn out to be the case that the player who is winning the game of NIM doesn't care about those moves. They will never make them as a part of the winning strategy. So what matters is that everything you could do in a game of NIM with 4 stones, you can do from this particular position. You can move to a position that has the number 3, and from this position you can again, as its own number is 3, there are moves to positions with numbers 0, 1, and 2, so you can pretend you are playing NIM on these values you have assigned to those positions. And now comes the main result of the usefulness of these numbers. And this is about what is called the sum of games. So suppose you are playing not just one of these impartial finite games, but you have there are the 2 players that are playing the game, and the game is played in a room. And within the room, there are tables. And on each of those tables, there is a game in progress. So for example, there can be a single pile of tokens on each of the tables. And on each of the tables, we are playing the game with the rules of standard 1-pile NIM. So when it's your turn, you can remove as many tokens as you like from this particular game. But of course, we are now playing this big game, the sum of games. And the game is played as follows. So whenever it's your turn, you enter the room, you choose exactly one of those tables, and then you make a move on exactly one of those tables, and you leave the room again. And then it's your opponent's turn. So this is the informal definition by picture of what it means to have a sum of games. And now we can see that the n-pile NIM, for example, like the 3-pile NIM, as I drew the picture here, is simply the sum of 3 individual 1-pile games of NIM. And this also gives you the intuition that you can take very simple games. So on its own, each of the simple games of NIM is very trivial to analyze. You just take everything and win. But if you do a sum of these very trivial games, you can suddenly get something that is very non-trivial. And you have the general game of NIM where you have to do the strategy with computing the bitwise XOR. And now the main result of Sprague and Grundy can be stated in 2 levels. The first level is how to analyze these sums of games. And the answer is that what you can do is you can individually, for each of the tables, analyze just the game that is played on one of those tables. And you can compute the Sprague-Grundy value of this particular position you have here. And if you know these initial values, then you can tell whether this entire sum of games is winning or losing by doing the exact same thing we did before. So if this position looks like a pile of NIM of this particular size, and all of the moves that were available in the game of NIM are available here in this particular game, and this one resembles a pile of this size, and this one resembles a pile of that size, then we are claiming that the winning and losing positions can still be computed by taking the bitwise XOR. And if it is 0, then it is a losing position, and if it is positive, then it is a winning position. And the proof would now be exactly the same as a combination of what we did originally for the normal NIM and a combination of what we did for the Northcote game. So when we are making this claim, you now have to show 2 of the things. So the first thing is that if it is a losing position, a blue one, where the XOR is 0, and you make a move, you have to create a red position. You have to create a position where the XOR is non-zero. And why does this happen? Well, you have to choose exactly one of the tables. You have to make a move on this particular table. And making a move always changes the Sprague-Grundy value, because this number does not appear among these numbers. So regardless of which move you choose, you move to a different number. And if you change exactly one of these numbers, the XOR from 0 will change to being non-zero. So If you are in a losing position, the XOR is 0, you are forced to put your opponent into a position where the XOR is not 0. And now comes the opposite side. And for the opposite side, we can just play nim, and we can ignore the extra move. So even though there is an extra move that will change the 4 to a 7 or change the 4 to a 14 for some position, if we are just playing the game of nim, we will always win, so we can ignore these moves. So if you are in a position in the sum of games where the XOR of this Sprague-Grandi values is non-zero, you can imagine then to be the nim pile sizes. So if you see 4 here, and 7 here, and the 25 there, you can just find the winning move in the game of nim. One of such winning move would be to decrease this 25 to a 3. And in this particular game, on this particular table, there definitely is such a move, because if this position has the number 25, it means that among the options you have in this particular game are an option that will put you into a position of size 0, of number 0, number 1, 2, 3, everything up to 24 has to be present here in order for this position to get the number 25. So in particular, you definitely have a move that will decrease this 25 to a 3. This is a move you will make in this particular game. And you have put your opponent again in the losing position when the XOR is exactly 0. So that's how the proof works. And in fact, if you are more careful about the analysis, you can now go through, instead of just showing this, that from a non-zero position you can always, there exists a move to a 0 position, and from a 0 all moves are forced to go to non-zero positions. You can now be more careful in the analysis, and you can show that if you examine all possible moves here, all possible moves there, all possible moves there, and do the combination of what values can and cannot be achieved, then you will find the discovery that if you consider this to be one single game instead of a sum of smaller games, so if you took this entire room and placed it onto a table for another sum of games, then for this particular position, if you analyze the Sprague-Grandi values, then the Sprague-Grandi value of this entire position, seen as one big game being played, is exactly the XOR of these small ones. So not just the 0 or non-zero value of the XOR is useful information, but the exact value of the XOR of the small positions gives you the exact value of the Sprague-Grandi value of this entire position. So what this means, when we do the proof, and I will not do it because it's just technical, you will have to trust me. But once you prove this, you can, at will, you can go between the viewing of a game like a separate independent pieces and the sum of them, or viewing them as a whole. And when we will go now back to the game on the daisy, you will see immediately what this means and how this applies. Okay, I will leave this up for now, and I will use the left of the board. So now we are back with the daisy game, and we are starting to analyze the positions. Okay, I hear a lot of murmurs, so before I start talking about the daisy game, is there something you would like me to explain one more time? Let's do it like this. I will do the example with the daisy game so that you can see how this applied on a specific example. And if then something doesn't make sense, then you can ask me questions. So what we are trying to do now is we are trying to determine so we have a general position of the daisy game. So we have already played the game a little bit, not necessarily using a good strategy. We are somewhere in between. Some of the petals have already been removed from the daisy, and when we currently look at it, it is divided into one or more some contiguous segments of various sizes, and essentially a daisy that is in some intermediate state like this is a sum of games, because each of these pieces of the daisy is completely independent. When it's your turn, you have to choose one of the pieces and then make a valid move on that particular piece you chose. There is one way of looking at it. And what will happen is, well, sometimes you will choose to remove just the petal from the end, and the number of pieces of the daisy will remain the same. But sometimes you will remove 1 or 2 petals somewhere in the middle of a piece, and the actual number of pieces will increase. And now comes the main result, how the Sprague-Grundy function can be used in analyzing games like this. So if we have a position on the daisy, the position can be uniquely described by the lengths of these segments of consecutive petals. So you can have like maybe 1, 7, 5, 3, and another 5. And this is then a position 1, 3, 5, 5, 7. We can certainly sort them because the order doesn't matter. Yeah. So any position of the daisy can be described as the length of the consecutive pieces of petals we currently have. And the game of daisy that looks like this can now be seen. Yeah, it's easier to visualize this as like straight segments instead of arcs of the petals. So instead of 1, 3, 3, 5, 7, we can imagine that we have a block like this, a block like this, a block of length 5, another block of length 5, and another block of length 7. So this is yet another equivalent way of viewing the position. And now, again, whenever it's your turn, you can either erase one single square somewhere, or you can erase 2 consecutive ones. So for example, you could make a move like this. And now, after making this move, instead of having a block of size 7, we can now see it as a new separate block of size 4, a new separate block of size 1. So this particular move will get us from position 1, 3, 5, 5, 7 to the position 1, 1, 3, 4, 5, 5. And so when we have a position like this, what I'm saying is that we can see this particular position as a sum of games. So it is as if we had a room, and in the room we had 5 separate tables. And on this table there is the block of size 1. On this table there is the block of size 3. Here is the block of size 5. Here is a block of size 5 and a block of size 7. And now, when we are playing the daisy game, what you do is you enter this room, choose a table, and on the table you chose, you make a valid move. This is still the daisy game. But now it is very visually a sum of 5 independent games. And the power of the Sprague-Grundy result is that in order to analyze this entire position and to determine the Sprague-Grundy value of this entire position, and by determining the value, we can immediately know whether it is winning or losing, 0 or non-zero. We just have to analyze these individual positions. And if we know the values for each of them, for each one continuous strip of paper or contiguous segment of petals, then we can compute the position, the Sprague-Grundy value for any general position. So all that we need in order to analyze this game is we don't have to analyze all of the 2 to the n possible intermediate states. We just have to analyze the n intermediate states that are contiguous segments of petals. So this is what we are going to do now. And now, when doing so, we will again be using this like transition between this is one single position, or this position is actually sum of smaller independent parts. And we can do this at any moment we like, because like the XOR, as the Sprague-Grundy theorem says, is always remaining the same, regardless of whether you use it as a big position or a small position. So let's start doing the analysis. So if you have exactly nothing, there are no moves left, and the Sprague-Grundy value of that position is 0. If you have exactly one block, the only thing you can do is you can remove the block. This puts you into the position with value 0, and therefore your value is 1. If you have 2 consecutive blocks, what you can do is either remove one of them, and this puts you into so the valid moves from this position are either here or to a position where there is nothing left. This position has number 1. This position has Sprague-Grundy value 0. You can reach 0, you can reach 1. The smallest value you cannot reach is 2. What happens with the strip of length 3? This is where it starts being interesting. Now, for a clever bit of erasing, I will preserve a strip of length 3. And now the valid moves are as follows. So you can eat one petal from each side. So you can definitely have a position like this. And we know that this has the number 2. You can eat 2 petals from each side. And then you'll have a position like this. And we know that the number of this is 1. And you can also eat the middle petal. So now you also have a move into a position that looks like this. You have 2 separate squares. And now what is the Sprague-Grundy value of this position? Yeah, we know that what we just created is from this one game, we have now created a smaller sum of 2 independent games. So in any future move, the player will have to choose which one of these is the one where they want to make a move and then make a move there. So we can just look at the value of this. This is 1. The value of this is 1. And the total value of the sum of these 2 games is 1 XOR 1, which is a 0. So we can reach a 0, we can reach a 1, we can reach a 2, and therefore our value is 3. And I will do one more example because now the pattern will break. So we have 4 consecutive squares. And if we have 4, now valid moves, you can create, it's an extra ugly one. We can create a block of size 3, this is a 3. We can create a block of size 2, this is a 2. So this was eating from one of the sides, either 1 piece or 2 pieces. If we eat exactly 1 piece somewhere in the middle, we will get a block of size 2 and a block of size 1, and this is 2 XOR 1, which is 3. And if we eat the 2 middle ones, you will get 2 separate pieces, and this is 1 XOR 1, which is a 0. So now we went through all possibilities to make a valid move in this situation, and we created new games with Sprague-Grundy values 0, 2, 3, and 3. So the smallest value that was not reachable among them is the value 1. And now, instead of having an exponential time algorithm that it has to explore all of the entire possible space of all of the configurations of the DAISY game, we can just continue this computation until we get to a segment of length n. And now, once we do so, we are able to analyze any position that has segments of length up to n just by taking these values and taking the bitwise XOR. And if you just do it in this naive way that I just described, the time complexity will not be exponential in n. The time complexity will be roughly n squared, because for each of these strips, you try all of the possible moves. And the possible moves are, there is n possible moves how to eat 1 petal, or n minus 1 possible moves how to eat 2 consecutive petals. So there are roughly 2n ways to make a valid move. Each of them will give you 1 or 2 smaller pieces of the game, and you can compute the Sprague-Grundy value of the game you just created, and then you just take the smallest value that doesn't appear among them. And yeah, if you are lazy and you just push all of these into a set, then you will get an extra logarithm from the set, but you can just use a normal array with booleans, because if you have k possible moves, then the smallest non-reachable value has to be at most k, right? So the best you can get is you can reach each of the values 0 through k minus 1 exactly once, and then k has to be unused, pigeonhole principle. You cannot have reach more values than there is a number of moves. So you can just use a bit array and then discard the values that are bigger than the end of the array or something like that. But in practice, the extra logarithm usually doesn't matter. So if I'm coding this and I don't care about the very strict time limit for any reason, I'm just pushing the numbers in the set and then iterating over the set because I'm lazy. All right, so this is the general idea how this can be applied. So whenever you see a sum of games, so a game that consists of several independent parts, the Sprague-Grundy theory is a very useful tool that can be used to analyze each of those parts separately and then combine the results of this analysis to get the result for the entire sum of those games. All right, we still have a few more minutes left. So for the few last minutes of the lecture, I will talk to you a little bit about what's beyond. So what is beyond is, first of all, the game of NIM. Yes? Yes. So I will not give you the answer, but I will thank you for the question, because the question is something I was planning to mention, and it's nice that you reminded me of doing so. So this is still not the end of the road, because yeah, there are problem setters that are acquainted, they're familiar with these Sprague-Grundy values, and as soon as you have them as a new tool in your arsenal, something that you can use to analyze games, you can still ask more complicated questions, because just like before, when we could look for patterns in the losing and winning positions and try to generalize those patterns into a statement about them, when you now can compute these Sprague-Grundy values for various game positions, it is also possible, but not guaranteed, that there will be some kind of pattern in these games, in these numbers. What happens to them as we increase the number of the petals on the daisy? Will the sequence somehow be periodic, or will there be some system we can describe? And if we can identify such a pattern, and then using induction usually we can prove such a pattern, then suddenly we can solve the game for even bigger values of n. We don't have to even do the computation, but because we know we have observed the pattern and we have proved that the pattern is there. So this is still a valid question to ask now. How big can we make the numbers? How far can we push the analysis like this? Are there any patterns? And I will leave it to you to play around with these games. One particular game you can try out when becoming more familiar with this technique is the game that was Grundy's original motivation. And this is a game, again, with tokens. But this time we are not removing them. We start with a single pile with n tokens. And when it's your turn, you have to choose exactly one of the piles you currently have. And you have to split it into two non-equal parts. So if you have a pile of size 1 or 2, that one is already done. You cannot have any valid move with that. If you have a pile of size 13, you can split it into 1 and 12, or 8 and 5. If you have a pile of size 14, you cannot split it into 7 and 7, because those will be equal, but any other split is allowed. And again, the question is how to solve such games. The answer is use the Sprague-Grundy values, so you just need to know the values for one single pile, and then if you have any intermediate state with many different piles, you can just take the values for those individual piles, do an XOR, and then you are done. But yeah, the question still remains, is there a pattern? How do the numbers behave if you compute the Sprague-Grundy values of a pile of 1, 2, 3, 4, 5, 6 tokens? Is this some well-known sequence? Is there some periodic something? And for some games, the answer will be yes. There is some periodic behavior. There is some specific pattern you can generalize. And for some games, the answer will be no, or maybe. We don't know. I don't see anything. Do you see anything? I don't. But maybe there is a pattern, and we are just stupid and don't see it. So have fun playing around with the games and asking this question about them. And yeah, so the question was what lies beyond. And even in the area of these combinatorial games, there are some like cute generalizations for you to think about. One of them, one of the very straightforward generalizations of a game of NIM is the game called Hack and Bush. And the game looks as follows. Imagine you have a ground. So this is like one large graph node, but I visualize it as a single line. And now you can have, let's start with bamboo. So we have bamboo stalks that look like this. And whenever it's your turn, you can cut any single edge, and whatever falls off the ground is removed from the game. So with bamboo stalks, this is clearly just directly the game of NIM. Yeah, the size of the bamboo stalk is the pile size, and you cut from the top to remove as many pieces as you like. But you can then ask what happens if you play the game with general trees. And if you are fed up with general trees, then you can do anything you like. You can have houses, the house can have a chimney, and so on. And you can play the game of general graphs like this that have cycles as well. And it brings some new questions about what to do with the cycles and their are some statements that have been proved about this, and we can analyze actually all positions in this game. Then it becomes even more interesting if you turn this impartial game into a partial one. So instead of having edges that anyone can cut, you can actually have edges of two colors. There can be red edges and blue edges, and we will have a red player and a blue player. And already with some just bamboo stalks, it becomes a very different question to ask who wins the game, who is the one forced to lose the game. So when analyzing games like this one, there have been some very clever people, and in particular the Bible of this game theory and this type of questions, really the book to read is Winning Ways for Mathematical Plays. This is by Berlecam, Conway, and Guy, and they do all kinds of crazy mathematical stuff with analyzing games like this. In partisan games like this one, where everybody has their own limited set of moves, it turns out that what matters is like a move advantage. So if you had like a game that consists of just separate segments, so these are the blue segments, and the blue player can cut any blue segment when it's their turn, and these are the red segments, and the red player can cut any one when it's their turn, then it's clear who is winning, right? So if there are much more blue than red ones, then the red one will eventually run out of moves they can make, and the blue one will then win because the red one is forced not to have a move. So there can be situations where one player is guaranteed to win. There can be situations like this one where, for example, in this situation it matters who starts, because the player who starts loses. And now you can assign similar like numeric values to positions that are more general like this, saying how many moves of an advantage one of the player has. But it turns out to be the case that the advantage is not always an integer. You can have like half a move of an advantage. And you can prove this by taking a position that consists of one copy of the half move, another copy of the half move, and then one move for the other player. And for this particular position, you can show that this is exactly the case, that it is exactly balanced. Whoever starts has to lose, because they will run out of moves first. So you can have half a move advantage, and you can have even crazier situations like this. So if you want to have fun with non-integer values assigned to positions in games, then look at these partial games and what happens in them. And then all of this is just one part of game theory, and this is the combinatorial part. And then you have another whole part that is sometimes called like just game theory, or maybe economic game theory, if you want to make a distinction. And these are games where the players do not take alternating turns. These are games where the players make a decision independently at the same time. The easiest such game, rock, paper, scissors. You are choosing one of three possible options, and at the same time your opponent is choosing, and based on what you chose, you will then get some payoff function. In rock, paper, scissors, one of you can win a point, or there can be a draw. And yeah, probably the most famous of these economic games is Prisoner's Dilemma. And this is the very famous game where usually it is presented in the Wild West setting. There are two guys, bandits, Butch Cassidy and Sundance Kid. They have been doing some crimes around the countryside, and suddenly the sheriff managed to capture both of them. And now the sheriff came up with a cunning plan how to get them to confess. So he locked them up in individual cells on the opposite sides of the sheriff's station. And he came to Egypt. So here's the situation. So we have Butch Cassidy and we have Sundance Kid. And each of them has two options. Either they will confess to the crimes they committed, or they will not. They will remain silent. And the sheriff doesn't really have any kind of like direct proofs that they were the ones that committed all of those robberies. So if they both remain silent, so silent or confess, and also silent or confess. And let's say this table is from Butch Cassidy's point of view, but for Sundance Kid it's exactly symmetric. So if we both remain silent, what happens to me is maybe I will spend a year in prison. If I remain silent, but my partner confesses, this is like the worst possible option. So what happens then? He will be set free, but I will probably spend my life in prison, or I may even hanged, or let's say that I will spend 20 years in prison to have a specific payoff. Of course, the situation is symmetric, so if I'm the one who confesses, then I will be set free. But here is the problematic case with if both of us confess, then we will have maybe 12 years in prison each, because we confessed to the crime and the sheriff is happy. So now Butch Cassidy, sitting in his room, is trying to analyze this game and trying to argue, like, what is it I'm supposed to do rationally? And he thinks, so there are two options what my colleague does. If my colleague remains silent, what should I do? Well, if I remain silent, I will stay in prison for a year, but if I confess, it's better for me, because I will be set free. So if my partner remains silent, it's better for me to confess. What happens if my partner confesses? Again, if I remain silent, I will be the one getting the penalty for both of us. And if I confess, it will still be bad, but it's still better than nothing. I will still be out of the prison sooner. So regardless of what my partner does, the rational choice for me is to confess. Where's the problem with this? On the other side of the building, Sundance Kid is just going through the exact same logical steps and also comes to the conclusion that the only rational choice, regardless of what Butch Cassidy does, for them is to confess. So what ends up happening, if both players are fully rational and do the mathematically optimal thing, is they both will confess, and the real winner of the situation is the sheriff. So he got the confession. So what happened here, this is a specific type of a two-player symmetric game from the economic type of game theory. And what both of them rationally converge to is the thing that is sometimes called Nash equilibrium. This is the magical words you may have heard previously, like in the movie The Beautiful Mind or somewhere like that. So Nash equilibrium is like the decision what to make in such a situation. In this particular case, the only situation from which neither player has an incentive to deviate is the strategy of confessing and getting the wrong outcome. So there are some life lessons to be taken from this, and one of the life lessons is sometimes trusting each other and cooperating can together give you a better outcome than you could get by just each of you acting rationally in your own interests only. So it's a positive message. But yeah, this is just a very, very beginning of a surface of what happens in analysis of this type of games. It is definitely not always the case that the optimal strategy is deterministic. If you take rock, paper, scissors, then the optimal strategy is clearly throwing rock, paper, and scissors, each with probability exactly 1/3. If you do anything else, if you deviate from the probabilities, then your opponent can exploit it by playing the thing that wins against you with the bigger probability. And this is exactly why then like normal human championships in rock, paper, scissors exist, because humans are notoriously very, very bad random number generators. So yeah, the players cannot generate rock, papers, and scissors really uniformly at random and mutually independent from previous throws. There are some tells, some patterns, repetitions, and players are kind of training on identifying what the other player does and exploiting it at the same time, trying to be unpredictable themselves. So it can be fun for imperfect humans to play rock, paper, scissors, but it would be very boring if you put a computer there, because if the computer can reasonably well approximate the probability distribution, there is nothing you can do against them. You can, on average, over many games, the best you can do is draw by being exactly random. And if you deviate from this equilibrium, from this strategy, it will just be punishing you. So it turns out that all of these two-player games have this type of an equilibrium where neither player has an incentive of deviating. One player can guarantee that their outcome will be at least this much, the other can guarantee that will be at most, and this is exactly where they will then meet in practice. So there is a whole other batch of mathematical results about the games that don't operate in alternating turns, but operate by taking steps at the same time. And yeah, so this is a very, very fascinating area, and it's at the same time it's an area where it is reasonably easy to start with. So I remember reading my first books about this at first results already when I was in high school, and you don't really need to know any kinds of too complicated mathematics. Maybe once you get to analyzing these games with multiple options and so on, then it starts to go somewhere into calculus and stuff like that. But before that, it should be very approachable already to high school students, and definitely if you are at the university. So if this is something you haven't seen before and it looks interesting, give it a read. There is also a book by Tom Ferguson that was originally published as his lecture notes on game theory. If you Google Ferguson game theory, you can probably find some older versions of those PDFs, and those are very well written, very readable. Yeah, I can probably share also a link with you as well after the lecture as well. So at this moment, are there any final questions for today? If not, then thank you for your attention. We will have lunch. After the lunch, we will have the first. Yes?
With only trees is quadratic.
I think you can, yeah, you can solve trees in linear time in the tree size, because there is like a specific principle. If you already know this program, the values for the individual subtrees, how to combine them into a single node. So you can just like traverse the tree once and recompute those values along the tree. So it should be doable in linear time. Okay, thank you for your attention.